Hello and welcome to physics. We are going to talk about light and reflection in this unit, and this will be the first lesson. I'm going to take you through a couple different things with basic reflection on flat mirrors, and then have you do an exit activity estimating your height and how much of a mirror you would need to see it. All right, so the first thing we're going to take a look at in this unit is a review of what light is. And light is part of the electromagnetic spectrum. And as you can see here, there are many different types of electromagnetic waves, anywhere from radio waves, micro, infrared, visible light that we commonly refer to as light, all the way up to higher energy, ultraviolet, X-rays, and gamma rays. And they're all categorized basically by their wavelength and their frequency. So when we talk about different types of light, we're really just talking about different types of frequency of those light. And visible light, like I said, is just a small fraction of those. All right, so when we take a look at an electromagnetic wave in general, what an electromagnetic wave is, it's an oscillating electric field and magnetic field. The electric field in this picture is symbolized by the pink wave, and you can see it's a transverse wave that moves up and down through the medium. The direction of the wave would be traveling to the right of the page. And the magnetic field is another transverse wave that runs perpendicular to it. So there are two transverse waves that are kind of melded together to make one electromagnetic wave. So how does this compare to some of the things that we've talked about already? Well, if we change the frequency of a sound wave, what we're doing is we're really changing what we know as the pitch. Well, light waves have frequency also. And when we change the frequency of a light wave, we're really changing the color. And just like when we talked about sound, changing the frequency or the pitch, the high and the low notes, didn't really make the sound travel any faster. It just was a perception of a high note or a low note. Similarly, if we change the frequency of light, it doesn't change the speed of light. It just changes the color that we would perceive. So what is the speed of light? Well, the speed of light in a vacuum is 2.99792,458 meters per second. Now that gets to be a mouthful, so we commonly just call that c as the speed of light, and we can use some scientific notation, 3.0 times 10 to the 8th meters per second. It's a constant anytime you have any light wave anywhere in the universe. If it's traveling through a vacuum, so empty space, it will be traveling at this speed. As you saw in the previous example, we can use equations that we're familiar with. We know that the velocity of a wave is the frequency times the wavelength, and it's the same for light. If we know the speed of light, the constant 3.0 times 10 to the 8th meters per second, we can then calculate a frequency for a given wavelength. Or if we know the wavelength, we can calculate if we have the frequency, we can calculate the unknown wavelength. This leads us nicely into a discussion about mirrors, and we're going to talk about reflection as a big part of this unit. So this lines up nicely when we talk about reflections off of a flat mirror, like you see here in this picture. We're going to need to know some vocabulary, namely, where is the incident ray, the ray that comes in, perpendicular line, we're going to call the normal, and where the angle that makes with the normal is the incident angle. The normal that it makes with the reflected ray is the reflected angle, or the angle of reflection. So this terminology we're going to use continually as we talk about rays in this unit and how light bounces off of things like a flat mirror. Always look for the direction of the arrow. I know it's coming from left to right. and then it hits the mirror and continues in that direction. So this is going to give us an example of what a reflection looks like into our eye. And we have to remember one fact: light travels in straight lines, and our eye is going to perceive that. So a light, an incident ray coming in, bouncing off the mirror, will go into our eye, but our eye will see that as a continuation of a straight path. So it's going to project that back onto the other side of the mirror. Because this is not an actual physical connection of light, it's a virtual image. It's something that's on the back side of the mirror. If you put your hand there, you wouldn't see anything projected onto it or a screen. So your eye sees it because it's projecting that straight line path of the light that was reflected from the object. So it sees it as if it was behind the mirror. The distance from the object to the mirror and the distance from the mirror to the virtual image is exactly the same. So for example, if this was 4 meters away from the mirror, it would appear as if it was 4 meters away for the virtual image. So on this slide, I'd like you to make a prediction. Could this person, given the mirror that's hanging on the wall, so it starts here and ends here, would they be able to see their feet? Now, that they're not going to be able to cheat and jump up or shrink down or anything like that, but just standing normal, would they be able to see their feet in this given situation? Make a prediction at this time. To help us better understand your prediction, we're going to talk about some virtual images. So let's say a person is looking at themselves in a mirror, and we know the light is leaving their chin, bouncing out the mirror, and coming into their eye. The eye projects that as if it was a straight line. So the chin would actually appear to be on the other side, like I'm attempting to draw here. So forgive my crude drawings. But that's not the only ray. There might also be a ray coming from the person's nose bouncing back into their eye. Once again, the eye is going to project that as if the nose was over on the other side from a straight line path. And similarly, if they're looking from their eye right into the mirror, it's going to bounce straight back. The eye will then project that as a straight line image right in front of where they're at. So as you can see, we're taking a couple key points on the person, their chin, their nose, and their eye, and we're trying to build what their image would look like. So I'm going to sketch in some remaining parts here. There's a crude forehead, some little bit of some lips there, a really elongated chin. And you can kind of see now we have this face, but this face is not an actual light collecting here. It's a virtual image, meaning that it's the extension of those rays from what a straight line would look like from you're looking at your eye. And like before, the distance from the person's chin to the mirror is the same as the virtual image distance, that what it appears to be on the other side of the mirror. Okay, we have enough information now to put this into some practice. So let's say we are looking at ourselves in the mirror and we want to draw a mustache. We know the angle of incidence has to equal the angle of reflection, so these two would be the same. We also know that the distance between here and here is halfway. So if I am looking and at halfway in between my eye and the top of my lip, that distance is 6.5 centimeters. But if I look at 3.25 centimeters halfway, I'll still be able to see what is on my upper lip, because that's where the light is coming from. So if I was going to draw this mustache, I would actually add the mustache at that distance, 3.25 centimeters down on the mirror, or 14.75 from the bottom of the mirror, and then it would appear as if it was on that person's upper lip. Okay, practically speaking, when you're trying to buy a mirror for your house, apartment, or wherever, you you really need to know if you're going to need the right length of mirror. You know, most mirrors come in certain set distances, like this one's 120 centimeters. Is that too long? Is that too short? That's $6. Should you buy 2 mirrors and connect them together if you're a really tall person, or could you cut it in half if you're a really short person and still get the same effect? So we can use this law of reflection to help us understand how much of a mirror we actually need in order to see ourselves from the top and the bottom. In this problem, we're actually going to do that. We're going to figure out how much of a full-length mirror we need in order to see the person's top of the hat and their shoes. All right, so we already talked about this idea of half of a distance. And so if I look here, I have 45 centimeters total distance, and half of that is 22.5. So if he looks 22.5 below the top hat, he's going to see the top of it. Now, the next thing we're going to want to take a look at is what happens with the shoes. So we can't use the total length of 207 in this case because it's not the full length of the mirror. If we were looking for the minimum length of mirror that we need to do, we're going to take the 207 minus 45 to get 162. So to get that length of a mirror, we're going to take the 162 and divide that by 2. So when we're finding our total length of the mirror, we're going to need to take that into account with 81 centimeters. All right, so I'm going to add then the 22.5 plus 81 centimeters, and I'm going to get a total length that I need of 103.5 centimeters. So when I'm looking at my mirror then, the total distance would be 103.5 from the top of the mirror to the bottom of the mirror. And that's all that they would need in order to see their shoe and the top of their top hat. Now it's your turn. I'd like you to estimate your height and then calculate a distance from your eye to the top of your head and figure out what would be your full-size mirror that would be needed in order to see the top of your head and your feet at the same time. Okay, this concludes our mini lesson on light and reflection, and we talked about full-size mirrors, and we also talked about the law of reflection, angle of incidence equaling angle of reflection, and we talked about some basics with electromagnetic and the spectrum. Thank you, and have a great day.